All right, so basic concepts of electrostatics continued. We're going to try to get through this worksheet. I suggest that you try all of these problems and see if you can find the answers. I will post the key at some point, but I want you to first give it a shot. So I'm not going to post the answers just yet. Now, this is page 7. So this starts on, let me change color. This starts on page 7 in the worksheet, and we're going to look at first insulators, conductors, polarization. Once I mention what insulators and conductors are and what is polarization, then you can try pages 7 and 8. So pages 7 and 8. All right. So the difference between conductors and insulators first. I think it's pretty obvious. In a conductor, electrons can move from atom to atom to atom. So let's say that you have some kind of a metal, and then within this metal you have a few atoms, and then each atom is going to have a nucleus, positively charged nucleus, plus representing the nucleus, and then you're going to have electrons somewhere on the outside. So I'm going to put some electrons on the outside, and if this is in fact a conductor, an electrical conductor, what that means is that an electron can move from atom. So let's say this electron here can be forced to move here, and it can continue to travel. Or in the next, this electron can be forced to move here, and then this electron can be forced to move here, and that's that. Electrons can move from atom to atom to atom. This is very specific to metallic bonds. I guess I'll give you a brief overview of a metallic bond. In a metallic bond, what happens is you have these atoms, individual atoms, that are more or less symmetrically spaced out, and you have the nuclei. Let's just put them like here, and maybe we'll do one more here, and then another row somewhere here. Now let's say that this is a slab of copper. So this is a slab of copper Cu, and copper has a specific atomic number. It's 29, so its atomic number is 29. What that means is that there are 29 protons and 29 electrons as well. So I'd have 29 pluses here representing 29 protons. I'm not going to draw 29 protons, but what I'm going to do is I'm going to draw a bunch of electrons. I need to have 29 of them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm not going to draw all of them, but you get the idea. So we have all of them, right? Then you move to the next one, and in the next one you also have a bunch of these electrons, and then in the next one you also have a bunch of these electrons, and then so on. The story continues. Every single one of these has a lot of electrons. They all have 29 electrons. So let's draw this. We have this sea of electrons, and now if you look at it, and I haven't even drawn all of them. I've probably drawn like a third of the electrons that I should have here. Let's just add some more. All right, so we have the sea of electrons, they're all over the place here. Okay, now when you look at this whole picture, what we have here is, it's very easy to find electrons which are in a place that is, so let's see if we can be lucky enough. Here's one. Take this electron. It's between this nucleus and that nucleus, right? And so to which one does it really belong? Or take this one. Right? It sits between this one and this one. So to which one does it really belong? Or take this one. This is even better. It sits between this one and this one. Which one does it belong? And here's another one. And then here's another one, and here's another one, and then here's another one, and we could pick another one here, pick another one here, and maybe we'll do another one here, and there should be something here, but I don't really see anything that I drew here, so I'll just leave it at that. The point is that there's a lot of these electrons. Most of these electrons are bound to their specific atoms, and there's nothing you can do about it. So for example, this one here, right, this electron here, it's not going anywhere. This one is stuck to the nucleus, it's not going to go anywhere. But this one here seems to be suspended between these three. It seems to be in some sort of an equilibrium. It would not be very difficult to push it out of this place. Just sort of kind of sits there, but it seems to be in equilibrium, versus this one is stuck to this nucleus. So the point is that you have these electrons, few compared to the number of total electrons, but you have them, and these electrons are sort of free to be pushed somewhere else. So for example, you could bring in a balloon. Let's bring in a balloon here. Good enough. There's a balloon. Let's say that this balloon is negatively charged. So with these electrons now, excess of electrons in the balloon, what will happen is these electrons will now exert forces on all of these electrons here. But most of these electrons won't be able to go anywhere because they're so strongly attracted to the nucleus. However, the few that are free will be able to move. So if you could yank this one out of here and then make it go to shift it a little to the right, so that it shifts a little to the right, then you leave some room for this one to jump over that. Then you leave some room for this one to jump over that. And so you can have sort of a flow of electrons where this one moves, and this one moves. So you have these free electrons, and the free electrons can move. Now there's a lot more to the picture than what I gave you, but I think it gives you a decent, gives you a decent idea here. So if you could get this one to move a little that way, if you can get this one to move a bit this way, leave this spot empty, then this one fills in, and then this one can fill in as well. And then maybe this one here fills in this direction. So because of the spacing, geometric spacing of the atoms, and because of the sea of electrons that you have there, and this is specific to metals, you will have these free electrons, and the free electrons will be allowed to move. That's the idea here behind a metal, behind a conductor, and electrons here can move. So conductors, electrons can move easily. All right, now in insulators, that obviously is not the case. I'm just going to put here for insulators, electrons cannot move easily. You can still force electrons to flow across an insulator. You can do that, but it will take a lot more energy than it would if instead you had a conductor. Now in the insulators, you're going to have, insulators would typically be plastics, wood, polymers in general, and there what you have is you have long chains of molecules that are complex structures, and the electrons are bound to specific atoms, and it is difficult to move these electrons anywhere. You don't really have a sea of electrons in polymers, and so it's difficult to move electrons from one atom to another. It's not impossible, but it is difficult. All right, so insulators, generally speaking, polymers, plastic, wood, etc. Okay, so we have that. Now, if you charge, what do we have there? Conductors. But okay, suppose you charge a conductor versus an insulator. So let's say you have a conductor here, and you charge this conductor. I think I mentioned that in the previous video. Anyways, if I did, then I did. If I didn't, then I didn't. But let's say you bring a bunch of electrons and you dump them in this spot, so that they're right here, and this is a conductor. Maybe you had a balloon, and the balloon had a bunch of electrons. You brought this balloon closer, and the electrons were transferred to this metal conductor. Within a few milliseconds, these electrons will move all over the place, right? Obviously, electrons similar charge, at same charge, they will repel each other, and so what's going to happen is these electrons, instead of sitting here, they'll push away from each other, and they will spread themselves more or less evenly, assuming the surface of the object is symmetrical. And so you'd get something like this where these electrons are spread more or less evenly, and they will just then sit there in equilibrium. On the other hand, if you have an insulator, there we go, good enough, insulator, and you dump a bunch of electrons in one place, that's it, they're stacked there. They won't go anywhere because this is an insulator. It is difficult for the electrons to move. Now, it is true that if you were to dump really a lot of electrons here, if you were to really force a lot of electrons in here, they would move at least a little bit. But right, it is much more difficult for the electrons to move. So this would be an insulator. This would be a conductor. Okay, now the concept of polarization. So you could polarize an atom. So for example, suppose that you have, how should I do it? Why don't we just first do a conductor? So a polarization of a conductor. All right, polarization of a conductor. Let's say we have a slab of a metal here. And how would we want to do? I guess we'll just do it like this. Here's a row of atoms. There we go. Each one has a positive charge, in the inside, and then you have electrons on the outside. I guess we'll put the pluses here. And then you have electrons around them. So we'll draw a few. All right, so you have negatives around these positive nuclei. And then let's say you take a balloon and you bring the balloon closer. So here's a balloon. You dump a bunch of electrons on a balloon. And then you take this balloon and you bring it closer and closer and closer. As you bring it closer and closer and closer, obviously what happens here is you exert a force on the electrons within the metal conductor here. So let's drop the balloon somewhere here. And what will happen here is these electrons will be forced to move, and they're going to move from one atom to another one. So this electron here will move in this direction, this one in this direction, this one here, this one will jump to the next atom, next atom, next atom. Is going to be this chain effect. And so the end result is that you have an extra electron on this end, or maybe extra 2 electrons on this end, or maybe extra 3 electrons on this end. And what you have is an electron or 2 or 3 that are missing from this end, which means that the left hand side is now positively charged. So the left hand side of this whole row is positively charged, the right hand side is negatively charged. But then of course you don't just have one row of atoms, you have many rows of atoms, right? Here's another row, and here's another row, and so on. And it's pretty easy to see that you end up with a whole wall here that is positively charged, and you end up with a whole wall on this side that is negatively charged. So generally speaking, if you have, and then the inside though, note that when it comes to the inside, you don't really have any uneven distribution of charges, because whatever moved away from one atom is what it gained from the other atom. And so you still have, this is a neutral, this is a neutral, this is a neutral, this is a neutral. All of these atoms are neutral. It's only the outside atom that has an excess negative, and the outside atom here that has an excess of positive charges, but the inside ones are still neutral. So the inside is neutral. So generally speaking, if you bring a balloon next to a metal conductors, then what happens is one side becomes positively charged and the other side becomes negatively charged. The inside, there's really nothing interesting happening here. If this is the picture you get, then this metal is polarized. This thing is polarized. The word polarized just means that you have an object that has positive on one side, negative on the other side. Right? It's polarized, it's split, it's divided in that sense. Now, polarization of an insulator. So you can polarize an insulator, but it would be, it happens a little differently there. So let's take a case where, so I'm gonna put here insulators. These work a little differently. Let's say we have a wall, and within a wall we will have atoms. In fact, within a wall we would have some sort of polymers, but let's just do, polymers are long chains of molecules, but let's just do the two columns that I have of these. And we do need the nuclei. I drew too many. But I guess we'll do it. So we have that, and then we have the sea of electrons around each one, right? So you have a bunch of negatives all over the place. And now what we're going to do is we're going to take the same balloon that we had there on the left hand side with the conductors, and we're going to bring it in here towards this wall, and we will try to figure out what will happen. So let's take the balloon, and we already have it drawn, so let's take it. There we go. And we bring it here, and we bring it closer and closer and closer and closer, but we don't let it touch the wall. All right, as we bring it closer and closer and closer, the electrons within the atoms will be affected. But they won't be able to move from atom to atom, right? An insulator wall is going to be an insulator, right? A wall is an insulator. This is slash insulator. So these electrons here cannot move to the next atom over, but they can still be moved within the atom. Like the electron cloud you're going to have a larger probability of finding an electron on the right hand side. So the electrons, some of these electrons that were on the left hand side relative to the nucleus, you can just redraw them on the right hand side and then get rid of some of these here. So this one's gone, this one's gone, maybe this one, maybe this one's gone, maybe this one and this one, maybe this one and this one's gone. Let's remove this one and let's remove this one and this one. Now they tend to be pushed away, but they won't travel to the next atom over. Something similar is going to happen with the next column, although the effect is going to be less pronounced. So fewer electrons will move. Still, they'll move, right? So you're going to end up with some more electrons on the right hand side. Well, the point is that when you do that, each atom becomes polarized. So now instead of having an atom where you have a plus and then you have minuses around it, now you have an atom where you have a plus and then you have minuses tending to sit on the right hand side. In other words, you can redraw this atom as just being plus and minus. So you've polarized each individual atom. And then note that what happens here is that you end up with a positive along the wall. So along the wall here you have positive, positive, positive. I'll emphasize the pluses. And then what is the charge of the balloon? Negative. Well, what's going to happen here is the balloon is going to be attracted to the neutral wall. All right. I may have mentioned this before. Okay, so we have, let me see if that was it for this piece. Yeah, so now you can pause the video and then you can try the problems on these pages here, pages 7 and 8, and then you can come back to the video and we'll move on to the next few concepts. Charging by conduction and grounding. These are pages 9 and 10. Now there's not that much here to say. I mean, the only thing really is going to be grounding that I sort of have to explain, but charging by conduction, this first thing here, charging by conduction, that's just dumping electrons by direct contact on some object. So let's say we have a conductor here and it's neutral, and I'm going to label this as conductor. And we want to charge this thing by conduction. To conduct means to basically touch it. And so I guess I'll put it here. To conduct. Conduct means to transfer something by touch. To transfer by direct contact. So you can conduct heat by touching a cold object to the hot object. You can conduct electricity by touching touching an uncharged object to the charged object. So let's take the balloon. Let's say the balloon has been wrapped with a bunny and it ends up having a negative charge. So we have a bunch of electrons here, and then we take this balloon and we bring it close enough so that electrons move. And now we have 1 and 2 and 3 maybe here, and we have lost this electron and this electron and this electron now. And then we remove the balloon and now we have these 3 electrons on a conductor. Of course, these 3 electrons will spread themselves. So if let's say one stays behind, then here's second and here's third one, and that's it, right? So by direct contact and in parentheses touch, that is charging by conduction. That's about it. Now grounding is a bit different. So suppose that you have an object and the object is here's the object, and the object has a certain amount of charge there. And let's say this is a metal sphere and it sits on top of some kind of an insulator. And maybe on top of a table. If you want to ground this metal, what that means is that you want to provide a path for the electrons to dissipate. If you provide a path for the electrons to dissipate away from this metal, then this metal is said to be grounded. So, let's say you bring in another big plate right here, and it's huge compared to this little metal, and then you take a little wire, and the wire runs and touches that. What's going to happen is now electrons will spread over this sphere and this metal, and let's say that this really is big. Not drawn to scale, it's just really, 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 really big, then most of these electrons will actually dissipate and they'll spread themselves evenly between this and that. But because this is much bigger, more electrons will sit here. So you're going to end up losing a bunch of these electrons. And let's say this one's gone, this one's gone, this one's gone, this one, this one, this one, and this one, and maybe this one. It's not likely you're going to get all of them out, but you will get most of them out. And now these electrons will evenly distribute themselves somewhere here. And again, this has to be much bigger so that the electrons can actually spread themselves over both surfaces. But because this is a bigger surface, more electrons would be here. All right, so if you provide a path for electrons to dissipate away from an object, then the object is said to be grounded. That actually was a pretty good definition of grounding. Let's see if I can repeat that. If you provide a path for the electrons to be dissipated away from an object, then the object is said to be grounded. That's good. All right, now this could work. Let me give you a bit of a twist. So let's say that you have a charged object, but now that the object is positively charged. In other words, you've removed electrons from it, and now it has a positive charge here. Right? It sits on top of an insulator on top of a table, and you want to ground it. Well, you do the same thing. You take some kind of a big piece of metal, and then you run a wire to it, touch it, and then the plasmas spread themselves. But it's not really the plasmas, right? What will happen here is the electrons within this piece here will be attracted to these positives. So the electrons will sort of flow in and then cancel this stuff out. So you're going to have like movement of electrons, where an electron from this piece here flows because attracted by the positive charge, then cancels this thing out. And another one flows and cancels this thing out, another one flows and cancels this thing out, and why not? Another one flows and cancels this thing out. And now this is neutral. You have grounded it, it's neutral, the charge is dissipated. And you have, because electrons have moved in this direction, right? So electrons moved in that direction to cancel out the positives, you end up with loss of electrons here, and therefore you have plus. There were 4 over there, now there are 4 here. So it works with both positive and negative charge, right? As long as you provide a path for the charges to dissipate, you have grounded the object. Now, typically, what happens is why is it that we use the word ground to ground something? Well, let's say you have an antenna, and the antenna sits out on a, some kind of a pole, say some kind of a wooden pole, and then this thing is embedded in the ground. And but you have the metal, the antenna itself is metal. Now you want to ground this thing. Let's say because you don't want, let's say that lightning strikes this, then you want that the charge within a lightning to dissipate somewhere away from the antenna so that the antenna doesn't get destroyed. Although probably would be destroyed anyways if it were to be hit. Well, maybe not, depends on how you ground it. But what you'd want to do is you would want to provide a path for the extra charge to dissipate. So then you take like a wire, and then you would run this wire around this pole and drive it into the ground. And you would want to drive it fairly deep into the ground, and at some point the ground is fairly conductive, and the deeper you go, the more moisture you have down there, the more minerals you have down there, salts and so on and so forth, and you end up with a conductive surface somewhere here on the bottom. So this bottom, the ground itself, acts like a big metal chunk that can absorb the charge from the antenna, and so in that sense we say this thing is grounded. Every house has to have by code a stick on a site that runs deep into the, I think it's like 9 feet that it has to go deep into the ground, and this must be connected to your electrical box on the inside of the house, so that any excess charge can be dissipated can dissipate into the ground. Excess charge from the house. Okay. So we have now grounding and conduction by charging. You can do pages 9 and 10. So pause this video, do pages 9 and 10, try to figure out the correct answers, and then come back. All right, so now charging by induction. These are pages 11 and 12. Same thing. Once I have introduced the concept, you can then stop the video and do pages 11 and 12. So charging by induction. So far you know of charging by friction, frictional rubbing of dissimilar objects. You know about charging by conduction, you know about grounding, you know about polarization, triboelectric series, and here comes charging by induction. So you can induce a charge. This process there are a couple of steps to this process. So let's move that aside. That should be plenty of room. Charging by induction. So let's say you have some kind of a conductor here. Some kind of a metal conductor, and it's neutral at first. So this thing is neutral at first. I'm going to put here in parentheses neutral, has no excess charge, no positive or negative charge on it. I mean, it has electrons as protons, right, because of the atoms. So there are billions of atoms, and therefore there are billions of electrons and protons here, but they cancel themselves out numerically, right? So this thing is neutral. Now let's say you take a balloon. Let's say the balloon is charged. So we have here a bunch of negatives, negatively charged balloon, and then we take this balloon and we bring it closer and closer. So I guess I'll do that, and it comes closer and closer, but it doesn't touch, right? It just comes closer and closer. At some point it just sort of stops there and doesn't do anything interesting. So this thing is going to get polarized, right, by the process I explained somewhere else. So we're going to end up with electrons moving to this side. We're going to have a bunch of negatives, and we're going to end up with lack of electrons on this side. Therefore, these are positives. That's it. Nothing on the inside. Nothing interesting happening on the inside. You just end up with positives here, negatives here. All right. Now, the next thing we're going to do is, while this thing is sitting like that, we're going to bring in a we're going to ground this side first. We're going to ground this side. So let's say here's a finger. Let's make sure that's not bad. That's pretty good. That's pretty good. And what do I want? This is what I want. Now we're going to take this hand and we'll bring it closer and closer and closer until we touch that side. By touching that side, what's going to happen is the electrons will flow into my hand. My hand is like my hand is conductive. It's not a great conductor, but a human hand is it's a decent conductor. So electrons will jump into this hand. Maybe not all of them. Maybe it's say 2. So I'm going to pick up 2 of these electrons and they'll come with me. Right. So I'm going to put them here. I have touched the metal. I've grounded the metal, and so the electrons came to the hand. And let's see. I have now 2 electrons here. Of course, what that means is that these 2 are gone. And this is basically it. Now what we do is we remove the balloon, and so let's do that. We get rid of the balloon. Let's just move it there. And now if you look at this thing, that charge is going to distribute itself more or less evenly. Right? So if I have pluses, minuses, well, first of all, what is going to be the net charge of this whole piece of metal? It's going to be positive, right? So now this charge is going to be positive because I have more pluses than minuses. So there's that, and therefore this thing is charged. Now this positive here and this negatives, they'll cancel themselves out, right? So you're going to end up with, let's get rid of this one, and that one's going to cancel themselves out. And then the 2 pluses, they'll distribute themselves evenly. So one will be on one side and the other one will eventually be on the other side. The point is though, that by doing this whole picture here, by going through this whole process, you end up charging this piece of metal, and it is now positively charged. That's process of charging by induction. So in induction, charging by induction, first thing that happens is you polarize a conductor. 2, then you remove the positive and negative charge by grounding this thing. So you ground the conductor, just remove some charge, like positive or negative charge. You can remove positive or negative charge, and that's it, and you end up with a charged object. Now let's do the same thing, but switch it up a little. So what we're going to do is, here's the metal. You take the balloon, you bring the balloon with a negative charge. Therefore, what that does is it splits up the charge here so that you have negatives here, you have positives here. But then you take the hand and you bring the hand, and this time you touch this positive side. So you have a that's interesting, 6 fingers. So you bring this hand to this side. I'm not gonna bring this hand in. I'm just gonna, I think you can picture this. So you take this hand, you bring it to this side, you touch it close to it. What happens then is that the electrons from your hand, because obviously you have electrons in your hand since you have atoms there, electrons in your hand, in your finger, will be attracted to these positives, and so they'll jump. These electrons will leave your finger, and therefore you're going to end up with an excess of positive charge here because you've lost some electrons. but then these electrons will move in and they'll cancel out some pluses. So since let's say 2 electrons jump, right? So then 2 pluses are cancelled out, and then 2 pluses are formed here in the hand, and now you end up with 2 pluses and 4 minuses. So this whole thing is now charged to a negative charge. There. All right, so this is charging by induction. This thing now has a net negative charge. These charges will distribute themselves, and so they'll look a little differently here. Like this minus, this minus and this plus will cancel out. This minus and this plus will cancel out. You're going to end up with 2 negatives here. So you're going to have 2 electrons is the actual charge, but it would be negative. Now, third option is something that is shown on page 12, I think. I'll just briefly mention it. Suppose you have a conductor here and then another separate conductor here, but they're in contact. So they are in contact. And then you bring in a balloon, negatively charged. What happens is you end up with negative charge all the way here and a positive charge on this side. And then what you do is you don't ground this thing, but instead, oh, that's good. But instead you remove that. And what do you get now? Well, a charged object. In fact, you get 2 charged objects. Let's deselect that. And so now this is also called charging by induction. Now you end up with this thing here being negative and this thing here being positive. Okay, so you can now do pages 11 and 12. See how that goes. And then the next thing after this, after charging by induction, is to introduce some math. So we'll look at electrostatic force, Coulomb's force between 2 charges. So you have a charge and then you have another charge. There will obviously be force between them, repulsive force in this case. And there's a way to calculate that force. Likewise, if you have 2 negative charges, you'll get the same picture. And the force, there will be force between them, and you can calculate that force. And of course, if you have a positive and a negative, then it's going to be a force of attraction between them, and you need to be able to calculate the stuff. And that was what we will do next, but that's going to come on Friday. Yeah. All right. Well, this will do.